Okay, so hello friends. So it's a pleasure to have Pinaki as a today's speaker for the our seminar series. So just to introduce briefly, Pinaki is in Okinawa Institute, um, and he directs the fluid dynamic mechanics unit. Um, he has his group works in turbulent flows, geophysical flows, atmospheric flows, granular flows. Before OIST, Pinaki was in University of Illinois at Urbana, and he collaborated with Nigel Goldenfeld, and I mean you can see from here Goldberg and so on. So Pinaki today is going to talk about turbulent friction drag, and we look forward to his talk. Okay, Pinaki, all yours.
Well, thank you very much, Mahendra, for the kind invitation as well as the introduction. I'm going to talk about this area that we call the spectral link. I'll introduce the basic concepts and illustrate with a few examples. This work has been kind of a focus of mine for over 15 years, and it's pursued in very close collaboration with my colleague at OIST, Gustavo Joya. There have been also other collaborators over the years that have participated in various aspects of this work. I should mention especially Nigel Goldenfeld, Walter Goldberg, and Hamid Kelly. Okay, the part of spectral link that I'll talk about today concerns turbulent frictional drag. And by means of a very quick introduction as to why one would care about turbulent frictional drag, let me just illustrate with two examples, one from nature, one from engineering. So here is a satellite image of a tropical cyclone, hurricane, typhoon, cyclone over ocean. And one of the crucial things one needs to know in order to predict the intensity of a tropical cyclone is the friction between the bottom of the cyclone and the ocean underneath. So the turbulent friction between this turbulent flow, the typhoon or the cyclone, and the ocean underneath is a crucial parameter to know and to predict the dynamics of a tropical cyclone. Okay, so that's one example from nature. If we take another example, let's say from engineering, so these are, for instance, gas pipelines or oil pipelines, and flow inside of gas of oil inside the pipeline is generally turbulent, and turbulent friction is the parameter that sets the pumping cost of fluids, turbulent flows inside pipes. Okay, so for various reasons, one is interested to understand and to predict the friction between a turbulent flow and a wall that surrounds the flow. And I'm going to focus on this pipe flow problem to introduce the main ideas. And let us imagine the following scenario. So we have a pipe of radius capital R, and this pipe, there's flow taking place from left to right with a mean velocity capital V. Now, in general, the walls of a pipe are rough, but I'm going to focus on a very special, simplified kind of roughness. It's a single length scale roughness. And one way to visualize it is to think that I have actually a smooth pipe that I have rendered rough by pasting onto its inner surface, let's say spheres of the same size, let's say of small r diameter. Okay, so what this does is that it makes the interface between the flow and the pipe wall rough with a length scale equal to small r. There is a turbulent friction, which is the main concern of this talk, that develops between the turbulent flow and this rough surface. And I'm going to denote that shear stress using tau. So the different dimensionless parameters that characterize this problem is the dimensionless velocity, the well-known Reynolds number, where nu is the kinematic viscosity of the fluid. There's a geometric parameter, which is the size of the roughness to the size of the pipe, which I'm just going to call as roughness, small r over capital R. And what in engineering literature is generally known as friction factor, small f, which is the shear stress made dimensionless using the kinetic energy of the flow. Okay, so these are the three dimensionless parameters that mainly characterize this problem. And what we know is that this friction factor is a function of Reynolds number and roughness. So to see what this functional dependence looks like, I'm going to show a very, very well-known set of experiments that date back to the 1930s from Ludwig Brandel's lab. It was his student Nikuradise, and these are very famous experiments that he did. I'm going to show his experimental data. On the y-axis, it's a log-log plot. On the y-axis is the friction factor. and in the x-axis is the Reynolds number. What Nikuradise did is he took pipes of 6 different roughnesses. These are 6 smooth pipes, and he rendered them rough by sieving sand grains so that these grains are of the same size, and then pasted those grains by hand to the interior wall of the pipe. So he has pipes of 6 different roughnesses by pasting different kinds of sand grains onto pipes of different radii. All right, so for these 6 different pipes, what he measured was the friction factor and plotted it against function of Reynolds number. When the Reynolds number is low, the flow is laminar. To experimental accuracy, all of the 6 pipes, the friction curve collapses onto the same bundle, which goes like this. And this is where friction decreases as Reynolds number to the power -1. This is the very well-known Poiseuille flow regime. But when you reach Reynolds number roughly of the order of 2000 or so, then suddenly this friction behavior changes completely. Instead of decreasing as 1 over Reynolds number with increase in Reynolds number, friction flips over and starts to increase with increase in Reynolds number. Initially, this increase is collapsed still onto the same bundle. The 6 different roughnesses, the friction curves corresponding to the 6 different roughnesses are on the same bundle. But when you crank up the Reynolds number more, that's when this plot becomes extremely interesting, and you see a plethora of rather interesting features. So this is the roughest pipe, the friction that corresponds to the roughest pipe. This is the second roughest, the third roughest, so on and so forth. Okay. So as you make the pipe smoother, you go further and further down onto this curve, and then you deviate away. All right, so you can see a number of features over here, and I'm going to direct your attention to the following 3 features. First of all, as we go from this region, which is actually transition to turbulence, and as we crank up the Reynolds number, we go through a local maximum over here, which I'm going to refer to as hump. After crossing the hump, as you make the pipe smoother and smoother, you're going to go across this line. And this is a log-log curve, remember? So this line, a straight line, is a power law. And another of Prandtl's student, Blasius, of Blasius boundary layer, fitted this data and empirically determined what the scaling of this power law is. So friction here for this smooth regime is only a function of Reynolds number, and the exponent is -1/4. So this is the so-called Blasius scaling. Eventually, as the Reynolds number is increased, you deviate away from the Blasius scaling and go to a local minima. And this local minima, I'm going to refer to as belly. And finally, for each of these rough pipes at high enough Reynolds number, we get to an asymptotic state where the friction no longer depends on the Reynolds number. It's an asymptotically constant regime. And this asymptotically constant regime, clearly the value of the friction depends on the value of the roughness. And if you plot the value of this asymptotic friction against roughness, voila, you see another power law where the friction does not depend on Reynolds number anymore, but depends on the roughness. And there is another power law, which is friction goes as roughness to the power 1/3. This is called the Strickler empirical scaling. I should note that it is very, very closely related. If your background is civil engineering, then you might know the same thing as the Manning formula. These 2 concepts are very closely related. Okay, so we see a plethora of rather interesting features where initially the flow is laminar in this regime over here. Starting from the point of transition to turbulence, we basically don't really understand much of what's going on. The laminar part we understand quite well, but starting from this point where we have this hump, we have the Blasius scaling, we have these bellies, and then eventually we have the Strickler empirical scaling. Where do these exponents of -1/4 and +1/3, where do they come from? What features give rise to things like hump and bellies? We don't really understand them. Okay, so that's going to be kind of like the leitmotif that is going to direct the different elements of spectral link that I'll introduce. But before I get onto spectral link, just to very, very briefly mention, it's obviously turbulent friction is something that is of immense importance, as I illustrated by 2 examples. So it's not that people don't understand anything about turbulent friction at all. In fact, there is a standard approach to predicting turbulent friction. And that standard approach goes back to the pioneering work of von Karman and Prandtl. So to just very briefly outline that approach, it's basically based on an indirect way. Instead of looking at the turbulent friction, Prandtl proposed, well, let's look at the shape of the mean velocity profile. So this is the wall, and this is the time average velocity at different distances from the wall. And he argued that if we introduce what is called a friction velocity, which is just the shear stress turned into velocity, and if we introduce that as a scale and we make some arguments that are effectively dimensional analysis arguments, we can come to the conclusion that there is a region of the flow where the mean velocity profile follows a logarithmic law. So this is the well-known log law. And what you would see in the log law is that the velocity scale is this friction velocity, which in turn is related with the shear stress of the frictional drag. Now, that's an explicit expression, but it has two constants. And these two constants are the von Karman constant, kappa, and the offset of the log law, p. There is no theory for it, so these are empirical constants. Taking forward from there, if we now go and make a consistency argument, which is to say that although the log law is only valid in a limited region of the flow, if we ignore that restriction and simply integrate the log law from the wall all the way to the center line, then we must have the geometric constraint that the integral of the velocity profile should be equal to the flux that is being communicated through the wall. And that argument effectively takes us to the point of this expression that you're seeing over here, where these constants A and B are related to the constants kappa and capital B. Okay, so what you get over here is an implicit equation that if I know these two constants, I can solve and get friction as a function of Reynolds number for the smooth wall flow. And this is the way people have been predicting friction as a function of Reynolds number for the smooth wall flow. And there's a variation of the same argument that can give you a prediction for a rough wall flow. But it does not tell us where the exponents of Blasius or Strickler comes from, or sheds no light whatsoever on bellies and hump-like features. So those are all very, very open problems. And that's what I propose to at least shed some light on using an approach that is not indirect, although this approach is very, very successful in terms of prediction. It is not indirect, but a direct way to get into grips with friction. And the approach that I'll illustrate, which is the approach of spectral link, is tied together with the idea of turbulent spectrum. So let me illustrate first with this sketch that I particularly like. It's the very well-known sketch by Da Vinci, where you have a jet of water plunging into pool and rendering the pool turbulent. And what you're seeing is the way Da Vinci showed turbulence. Instead of showing some bubbles or some sort of a mess over there, Da Vinci, using a theorist's eye, in fact, showed the mess of turbulence to be a superposition, an assemblage of rotating elements, let's call them eddies or vortices, of different sizes, from things that are very small to intermediate size to eddies that span the whole size of the pool. It's a superposition of all these eddies that makes the mess of turbulence. Going forward many centuries, we come to Kolmogorov, who gave us a phenomenological theory to describe the energetics of these eddies. So this is the very well-known idea of energy cascade that Kolmogorov developed based on prior work by Richardson and Taylor. Okay, so what's the idea of energy cascade? I'm sure all these things are very familiar, so I'll go through them rather quickly. The notion of energy cascade, just for our reference, is that energy is being communicated, let's say from the mean flow onto the largest eddies in the flow. And I'm going to denote the largest eddies in the flow to be of the size of the pipe, capital R, and its velocity to scale with the mean velocity of the pipe flow, which is capital V. These large eddies are unstable, so they split and communicate their energy to smaller eddies. I don't mean it exactly as splitting into half, although there is evidence that it's not too far from half. But these energies communicated into smaller eddies, which in turn are unstable. They keep communicating into smaller and smaller eddies until you reach to such small sizes that you can no longer ignore viscosity, and the energy, the kinetic energy, is dissipated viscously. So this is the idea of an energy cascade. And for this notion of the energy cascade, the key thing is to realize that what is conserved in a statistically stationary state across these different sizes is what Kolmogorov denoted with the symbol epsilon, which is the turbulent power or the turbulent kinetic energy per unit time per unit mass. So the epsilon is the quantity that is conserved across the different scales of the cascade, injected at the larger scales and dissipated at the smaller scales. Okay, so if I take any arbitrary eddy from this cascade of size s and I denote its velocity with us, then just to get to grips with epsilon, the kinetic energy per unit mass is going to scale as us square. The time scale of instability of this eddy, the only dimensional time scale we can form out of these two, is going to scale with s over us. Therefore, epsilon, which is the kinetic energy per unit mass per unit time, k over t, has to scale as us cube over s. That's any arbitrary eddy in any level of this cascade. But of course, the notion of the energy cascade is that this epsilon at any step of the cascade actually is set by the largest eddies. So we then argue that the epsilon is set by what is called the Taylor scaling, which is the largest eddy, capital V cube, its velocity cube, divided by the size of the largest eddy, which we argued would scale with the radius of the pipe, r. So I equate these two expressions, and that gives me immediately a simple looking expression that tells us if you give me the size of the eddy s, then I can tell you what its velocity is going to be just by equating the epsilon together. One of the things that I will use from this, other than this expression itself, is the idea that you can see right over here, is that the larger the size of the eddy, the larger its velocity. Another thing that we can infer from here is the very length scale where this cascade stops, so-called Kolmogorov scale. And we can infer that by arguing that the local Reynolds number based on this viscous length scale or the Kolmogorov scale, which I'll denote by eta, should be where viscous effects and inertial effects, after all, Reynolds number is a ratio of inertia to viscosity, is of order 1. And if I substitute this expression in here, we immediately come to the point that this smallest length scale in the energy cascade goes as Reynolds number to the power minus 3 over 4. Okay. So Kolmogorov's picture gives us two things. One is this expression over here that tells us what the velocity of an eddy is at any level of the cascade. And the second thing that it tells us is what the Kolmogorov length scale or the viscous length scale or the bottom cutoff of the cascade is. Okay, armed with these ideas, let's go back to the problem that we started with, which was turbulent flow over a rough pipe. This is, of course, an extremely complicated problem. So what I'm going to do is to drastically, brutally simplify this problem and see, using an utterly simple approach, can we shed some insight into what's going on in the problem? So the first level of simplification that I'll introduce is that all of this complicated turbulence that's going on in the pipe, I'm going to describe it using the Kolmogorov ideas that I just described. So the mean velocity of the flow is capital V, and that's creating or making conditions for this turbulent cascade, this energy cascade, whose large velocity goes or scales with capital V, and its size scales with capital R. So that's the turbulence that I'll consider. Now, this turbulence is confined by this rough pipe. So this turbulence is the fluctuating part of the flow. It is superposed on top of a mean velocity profile. And for the mean velocity profile, I'm going to focus on this region at the interface between the roughness and the flow above. And I'm going to introduce another drastic level of simplification by arguing that if I consider the mean velocity, then because of the roughness, there isn't a mean flow that's taking place left to right across here. So the mean velocity in this region, which I'll call cove, which is sheltered by the roughness, is quite small. On the other hand, away from the roughness, there is a mean velocity like a highway with the cars passing through where the velocity is higher. Of course, there's a whole velocity profile going from 0 to higher values all the way up to the center line. But as another level of drastic simplification, I'm going to take this whole mean velocity outside to be a single block that's moving from left to right. Mass conservation then tells us that if it's a single velocity that's moving from left to right, it has to be, the velocity has to be equal to the mean velocity of the flow. And here, the mean velocity is 0. So I am basically binarizing the mean velocity of the flow. In the cove, the mean velocity is 0, therefore the momentum is 0. And outside the cove, in the outer stream, I have the mean velocity capital V, so the momentum is rho times capital V. I have a contrast or a jump of momentum across this interface that straddles the cove and the outer stream. And right now, we'll focus on the regime of high Reynolds number. So in this regime, I have this very high velocity going like a plug flow in the outer stream and no mean velocity over here, with the momentum contrast being rho V minus 0. Of course, that's the mean velocity, but you have turbulent fluctuations superposed on this mean velocity, and effectively the same idea as eddy viscosity, or for that matter, kinetic theory of gases. You have the notion that these fluctuations are mixing low momentum region and high momentum region, and it is this exchange of momentum that is ultimately creating the shear stress. In other words, your shear stress tau is equal to the contrast of momentum, the change of momentum, rho v minus 0, multiplied by the rate of transfer, which is the velocity of the eddy. So if I have an eddy of size s, some arbitrary size, then if I denote its velocity by us, then the shear stress that is affected by this eddy is going to be equal to rho v multiplied by us. Remember, when we're talking about Kolmogorov, larger the size of the eddy, larger is the velocity. And we have eddies here all the way from Kolmogorov scale to much, much larger eddies. So we have momentum transfer as a combined effect of all of these eddies. But if we ask which eddy is going to dominate the transfer of momentum, then it's not going to be the smaller eddies, but it's because its velocity is small, but it's going to be the largest eddy, but not the largest eddy in the flow, but the largest eddy that can fit here. And this is where the single length scale roughness comes in very handy, because the length scale is single, small r. The gap size is also going to be determined by that single length scale roughness, small r. In other words, what I'm arguing based on geometry is that the dominant eddy, the eddy that dominates the momentum transfer, is of scale r. Eddies that are smaller than this have lower velocity. Eddies that are bigger than this do not fit here, so only a component of it contributes to the momentum transfer across this dotted interface. Okay, so now we have all the basic ingredients of this very, very simple model, where we are basically arguing that the shear stress scales as rho v times us, where us is the velocity of an eddy of size s. And for this very high Reynolds number flow regime, the dominant eddy that affects the momentum transfer scales with r. I've put it equal to r, but there could be a geometric factor there. So it scales with r is what I mean there, really. Okay, so once we have that, let's put together all the different elements of this very simple approach and see where we can go. So tau goes as rho v times us is what I argue. If I now go from tau to friction factor, use the definition of friction factor, which is divided by rho v square, what we basically then get is that the friction factor F scales as us, the velocity of the dominant eddy, divided by mean velocity of the flow. What do we do for the velocity of the dominant eddy? We use the Kolmogorov energy cascade picture. So we have an explicit expression for velocity of eddy, any eddy of size s. You substitute that in here, and you get the expression that friction is now set by the size of the dominant eddy, normalized by the radius of the pipe to the power 1/3. Well, you can already see where Strickler is coming from, because for a Rough-wal, very high Reynolds number, we argued that the eddy that fits and affects the momentum transfer is something that scales with r. Therefore, friction, S is going to scale with r, is simply the roughness to the power 1/3, where note that this exponent 1/3 is but tied to Kolmogorov's idea of energy cascade or epsilon being conserved. But what about a smooth wall? You immediately see a contradiction, because for a smooth wall, the roughness goes to 0. And this simple model would then tell us that friction goes to 0. In other words, smooth wall has no friction whatsoever. It's a frictionless flow. That is, of course, an absurd conclusion. So something's gone wrong. Well, if we think a little bit about it, recall that R can be made arbitrarily small, at least in principle. But S is the size of a physical eddy. And S cannot be made arbitrarily small because S is bounded from below by the Kolmogorov length scale. You can keep reducing the roughness as much as you want, but you cannot keep reducing the size of the eddies. At the smooth limit, you basically are bounded with S equals eta, or S that scales with eta. So the smooth limit should be thought of where the S is not equal to 0 because it's not possible, but S scales with eta, which Kolmogorov's theory itself tells us goes as Reynolds number to the power minus 3/4. Substitute that in here, and you can already see with your eyes that this 3/4 and 1/3, the 3 cancels out, and you get friction scales as Reynolds number to the power minus 1/4. This empirical exponent of Blasius, we argue via this very simple model, is but inextricably tied to the Kolmogorov exponent of minus 3/4. These two are tied together just like the Strickler exponent is tied together with the Kolmogorov's picture of energy cascade. So we can, for the first time, try to, in this rather simple way, understand where these empirical scalings of Blasius and Strickler are coming from. But we can go even further, again, using this very simple idea. Let us see. So we have basically these two asymptotic limits, high Reynolds number rough flow and smooth flow. So if we wanted to see how the flow transitions between one to another, we can then argue that the dominant eddy is some combination of the two. And here I'm just using a linear combination, but you can use all kinds of other combinations. The results more or less are going to be quite similar. The key being the asymptotics have to be right, meaning where roughness is going to 0, S scales as eta. And when Reynolds number is going to infinity, eta is going to 0, S scales as R. So you are going to go back to the Blasius scaling and the Strickler scaling, and you're going to see the transition between the Blasius and the Strickler scaling. And what you immediately see is that, well, of course, by construction, we get the asymptotics right, but none of the interesting features, specifically bellies and the hump that we saw in Nikuradise's data, are evident here. In fact, here, there's a monotonic transition from one regime, the Blasius, to the Strickler regime. So it may well be that the theory or this model is so simple that is incapable of capturing it. Or it may be that the model is missing something rather crucial, but if we add that, we'll be able to start to make sense of the other things. Well, it's the latter, and I'll show you how. Now, to show that, I'll have to slightly change my perspective and introduce the same ideas that I introduced before, but use the language of spectrum. Okay, so I'm going to use the notion of energy spectrum, which I'll denote by E of k, where k is the wave number. And the idea is, if we know the energy spectrum, it's simply a function that tells us, it's like a probability density function that tells us about the distribution of kinetic energy in the eddies of different sizes. Put differently, if I integrate this energy spectrum from any size 1/s to infinity, wave number k scales as 1 over the size of the eddy, then I get the kinetic energy that corresponds to that specific eddy size. For the inertial range spectrum, this is the famous Kolmogorov argument of -5/3 law. If you argue using dimension analysis that E of k depends on only k and epsilon, then this is the only combination that's possible. And if we substitute for epsilon the Taylor scaling, this is what we are going to get. You take this expression, substitute back here, you get the exact same thing that we argued before, because this is exactly the same argument. The first argument I gave in real space, this is the argument in spectral space. So why do I introduce this energy spectrum? Well, because it provides us with a very convenient way to actually see the shape of the spectrum in real flows and see what's been missing in the model that I've described so far. And just to put one more step, the idea that the friction scales as the velocity of the dominant eddy over V in this language of the energy spectrum now can be expressed this way. And you can here clearly see that friction is but a transform of the spectrum. If you give me the shape of the energy spectrum, I can predict the friction. Okay, so how does the energy spectrum look like? So here are some measurements we did with airflow in a rough pipe. And this is the region. So this is E of K versus K, again, a log-log curve. And the blue lines are the different energy spectra that we measured. And there is this region of intermediate size where you're not too large or too small. In this intermediate scale, what is called the inertial range, you do see energy spectra that conforms nicely with a k to the power minus 5/3 slope. But as you go to large K or small size of eddies, you have rather rapid, almost an exponential drop off of the spectrum. This is the so-called dissipative region of the spectrum. Likewise, when you go to small K or large eddies, after all, this is bounded by the geometry of the pipe. So you cannot have a power law that continues forever. So there is saturation that takes place. And these are called energetic corrections. In other words, so far what I have described, assume that the inertial range would extend throughout the spectrum. That's too simple an assumption to really make a lot of progress. Therefore, now we need to account for what is the effect of the dissipative correction and what is the effect of the energetic correction, which is what I'll do next. So what I'm going to do first is to account for the dissipative range correction, where in this E of K, I have the inertial range, and I also account for the dissipative range, where the dissipative range kicks in at a wave number that scales as 1/eta. So once we account for this correction, there are different models one can use, and the results are rather robust to whatever specific model that you use. The model that I use is called power model, but you can use a very simple exponential, and the results are very similar. Okay, so I substitute this new form of the spectrum, inertial range with dissipative correction, onto this expression of the spectral link, and I simply calculate what the friction is and plot it against a function of Reynolds number and different roughnesses in a Nikuradise-like plot. And what I find is this. Again, I get the asymptotics of Blasius and Strickler as is, but now there's a non-monotonic transition between these two regimes. And in fact, what you get are those bellies. And these bellies are but inextricably tied to the dissipative range correction of the spectrum, because the eddies that are dominantly affecting momentum transfer here are affected by the dissipative correction. And therefore, you're going to see these bellies. So we can now understand from the spectral perspective what its manifestation is of the dissipative correction onto the behavior of the turbulent friction. And we can take it a step further and go for the full blast approach to this, where you have the whole spectrum, inertial range with dissipative correction kicking it at a wave number going as inverse eta, and an energetic or a geometric correction kicking in at a wave number that scales with 1/r. For this whole range of spectrum, we can again calculate using this very simple expression that we had derived before, and simply plot what the theoretical version of the Nikuradise plot will look like, and this is what it looks like. So you can see now, we in fact even get this elusive hump. In other words, using the whole form of the spectrum and using rather simple arguments with lots of simplifications, admittedly, that effectively capture the notion that turbulent shear stress comes but from the transfer of momentum due to turbulent eddies, we can connect turbulent friction with energy spectrum. And this is the prediction from it. You get the hump, you get the bellies, you get this scalings, which were empirical till this point, of Blasius, the smooth scaling, and Strickler, the rough scaling, where the exponents of these scalings are but tied to the 5/3 exponent of the Kolmogorov spectrum. So this was effectively for us a starting point. At this point, it was 15 years ago, where we made this attempt to try to understand Nikuradise's features, Nikuradise's diagram, and try to use this kind of a simple model to try to understand where these different features come from. So once you have this background, you can then start to build on this background and make new predictions and explore new problems. And I'll briefly describe some of the problems that we have explored since. Now, For that, we simply generalize the ideas that I described to you. In the things that I said, the main concept is that if you give me the form of the energy spectrum, I can predict what the form of the friction is going to be. In the Kolmogorov picture, the spectrum has the spectral exponent with E of k going as k to the power minus 5 over 3. But I could get some kind of a generalized spectrum where, for whatever reasons, you have a spectral exponent that is different than 5 over 3. I'll denote it with alpha. So alpha is going to be my spectral exponent. I can just substitute it back here and do the very simple calculations, for instance, of generalized Blasius and generalized Strickler, generalized smooth wall and generalized rough wall scaling. And what we find is, for the smooth wall, friction scales as Reynolds to the power an exponent which only depends on alpha. If alpha is 5 over 3, this exponent is minus 1 over 4, the typical Blasius exponent. But if alpha is different than 5 over 3, then we can a priori predict what the frictional exponent is going to be. Likewise, for the generalized Strickler or the rough scaling, you have friction goes as roughness to the power an exponent that purely depends on alpha. If alpha is 5 over 3, this exponent is 1 over 3, the standard Strickler exponent. But for a different alpha, we can again a priori predict what the exponent is going to be. Okay, so this is going to be the basis of some of the new things that we have explored. In other words, what we want to do now is to look at flows where I can modulate alpha in different ways. Now, there are many ways to modulate alpha. So for example, you could add polymers, bubbles, all kinds of things onto the flow and then change the spectral exponent, or you could play with geometry. The flow that I described its three-dimensional flow in a pipe, but if you go to quasi-2D or two-dimensional flows, then there are new aspects of the spectrum that come in that now lets you play with alpha. So that's what I'm going to describe to you now. So the way we achieve this quasi-two-dimensional flow in a laboratory setting is the so-called soap film channel. This is an idea I learned from the late Walter Goldberg, who was an expert and a pioneer in using soap film turbulence to study two-dimensional flows. Okay, so the idea is the following. It's actually a very, very simple experimental setup to construct. So we take distilled water. You can just take tap water, it works just fine. And you add dishwasher detergent, typically a 2% solution, onto the water. And here's a schematic of the setup that you can see over here. Here's a bucket where you have this 2% solution of soap, dishwasher detergent in our case, added with water. We release that through a valve onto fishing wires. So this is a bucket that's sitting on some height, and from a valve, we are releasing this soapy solution onto two nylon fishing wires. What is going to happen is, at the apex of this triangle of the fishing wires, you're going to release the soap solution, and it's going to stretch itself into a film driven downward by gravity. The thickness of the film can be very small, of the order of 5 to 10 microns. But you can make it quite wide, of the order of a couple of centimeters, and really tall, of the order of a meter or more. So we effectively start from a very small point and guide it out to whatever width we want. And at that point, we introduce the two walls of the channel. For reasons I'll describe shortly, I'm going to make one wall smooth, one wall rough, and my focus initially is going to be on the smooth wall because I want to check the generalized Blasius scaling. And you can actually make both walls smooth, but I'll tell shortly why we made one wall rough. And so the flow goes down between these two parallel walls. And at the end of the channel, you collect it back using nylon wires onto another bucket. And then you use a small pump to push this thing back. And here you have a recirculating channel flow. But this channel is quasi two-dimensional because the thickness of the channel is orders of magnitude smaller than its width and its length. All right, so what do we do? To make the flow turbulent, at the entrance of this channel, we basically put a grid, which is actually a comb. We pierce this soap film with this series of rods over here, and they shed eddies, which we are visualizing here using thin film interference. And more important, these eddies conform to a very different kind of a spectrum than the Kolmogorov spectrum. It's the so-called Enstrophy cascade. This was theoretically predicted in the 60s by Frictional and Batchelor.
Pinaki, just one question. Huh?
Yeah.
So these rods are transfers to the film,
Yes.
So that works fine. I see.
Yes.
Just sticking it out there. Oh.
Exactly. And so basically the film is a plane that's going down, and these rods, this series of rods, we are poking the film perpendicular to the plane of the film. Great. And therefore the film goes through the rods, around the rods, the eddies are shed from the rods, and it's these shed eddies and really the decaying turbulence from that shed eddies is creating this Enstrophy cascade. So so then we measure the energy spectrum across the whole width of the channel. And here are some of the spectra that we measured from very close to the wall to the center line. And we find that there's a pretty big region of k to the power minus 3, confirming that just as expected from theoretical arguments, the spectrum conforms to Enstrophy cascade. For our purposes, wherever this comes from, the charm to us is that we get an alpha, the spectral exponent, that's very, very different than the usual 5/3. So what we do is we measure the shear stress on the smooth side, which we measure by measuring the mean velocity profile. If you're interested in the technical details, I can talk about that later. But basically, we use the technique of laser Doppler velocimetry. And we take this shear stress from which we compute the friction factor. All right. So the prediction for the spectral link is that friction should go as Reynolds number to the power minus half, not minus a quarter, but minus half, because the spectral exponent is different than 5/3. And here is our data. So here is log of friction, here is log of Reynolds number, and here's a whole bunch of data that you can see. The data that is with these triangles are actually with two smooth walls, and the data that you're seeing with this kind of squares, they are with one smooth and one rough wall, but we are measuring the friction only on the smooth wall. So it's the nature of the wall that counts, not the other wall at all. And in every single data point here, we verified that the spectral exponent is 3. And as you can see, for more than a decade in Reynolds number, the friction scaling goes very nicely in confirmation with the theoretical expectation and quite different from the -1/4. Okay, so now let me address the question, why didn't we just use two smooth walls? In fact, here I'm showing with both, but use one smooth and one rough wall. Well, the reason for that is the following. Two-dimensional turbulence allows for Enstrophy cascade, but it also allows for a different cascade, which is called the inverse energy cascade, where curiously, instead of energy flowing from large to small scales, it flows from small to large scales, and epsilon is still conserved, so the spectral exponent is again 5/3. The way one generally achieves in two-dimensional turbulence inverse energy cascade is to force the turbulence in the so-called forced turbulence scenario. And that's what this rough wall, we believe, is doing. So if I don't introduce a comb at the top, and I simply have this rough wall, as you can see from these images, is going to create very small scale turbulence around those rough walls. And what we do, and that turbulence is going to slowly diffuse out. But to increase the diffusion or to hasten the diffusion, because otherwise you're going to need a very long channel, what we do is we stick a very big rod, again perpendicular to the plane of the film. This rod sheds large vortices, which you can see over here, which sequesters the turbulence created by this rough wall and then just spreads it all across. And this forced turbulence conforms to the -5/3 scaling, as is again expected from Kraignan's theory. So we can confirm that just by changing the entrance of the channel, we can make the flow switch to one of two theoretically possible spectral exponent, 3 or 5/3. Rest of the techniques are exactly the same. The channel is exactly the same. All we are doing is playing with the entrance so that we can pick one or the other. It's like you have two basins of attraction and you're picking one or the other. So now if we pick the inverse energy cascade scenario, then of course, from the simple model of spectral link that I described, you're going to have the same exact scaling as in the Blasius case because the spectral exponent is the same. And indeed, that is precisely what we observe. So if I take now, again, for about a decade of Reynolds number, and I plot the friction against a function of Reynolds number. So here are different data. These are data that were taken in Walter Goldberg's lab as well as Hamid Kelly's lab in Bordeaux. And they conform quite nicely and fit nicely with the scaling of -1/4. So in the same channel, you have two different families of friction behavior, either -12 or -1/4. And the only difference between the two, because actually the channel are exactly the same, is the difference in the inlet condition. And the only thing the inlet condition changes in the inlet condition induces in the flow is the change of the spectral exponent. So
Pinaki, let me ask this question again. So just go to that inlet condition. So Cracknell theory is like you get phi-3 to the left of forcing wave number.
Yes.
Okay.
Yes.
So where is the forcing wave number? If you put 1, then are you increasing the forcing wave number? I mean, from that perspective, can you comment on that part?
So that's a very good point. And actually, forcing wave number, we believe, is at a scale that is smaller than the roughness. Because in the LDV, so these are the LDV data, you can see the phi/3, but the LDV signal saturates.
Okay.
And we have not been able to pin down what the forcing wave number is in this experiment. However, we did some simulations where we forced turbulence at a given wave number, and we were able to verify it. But in this particular experiment, what the value of the forcing wave number is, we know what the upper limit for it is, but we don't know what exactly the forcing wave number is.
I see. Okay. And regarding the -3 spectrum, the forcing should be at the, basically somewhere at k equal to 100 or something, right? Here, because
yes. So here actually we have a better sense because here it's really the space between the rods.
I see. Okay.
There may be an effect of the size of the rods also, but by and large, it's the space between the rods that determines this forcing wave number.
I see. I see. Okay.
But
great.
But yeah, here we only have an upper limit to it. We don't know the precise forcing wave number.
Okay. Great.
Okay.
Go on, please. Thanks.
So here, with these two families that you can see, you can immediately conclude two things. One, that friction, the relation between friction and Reynolds number, they are clearly two different families, and what's different between the two families are the spectral exponent. So this relationship is set by the spectral exponent. And the second is that the classical theory, due to Prandtl and von Karman, in that classical theory, there is no input, there is no contact with the turbulent spectrum, and that if we use any version of the classical theory, we are not going to get these two families because insofar as the classical theory is concerned, there is no direct effect of the spectrum. So the classical theory we suggest is in fact incomplete. Okay, so let me now just describe very briefly some of the recent results that we obtained for the rough case. So far for the two-dimensional case, I described about the smooth wall, which is technically simpler, but the rough one is technically quite challenging, and it took us quite a long time to get reasonable results. So here is the basic setup, exactly the same as before, but now we have both walls that are rough. Here is an image of thin film interference again, and here's a bunch of combs that are sticking through, and the decaying turbulence from this comb creates the -3 spectrum. And this -3 spectrum is across the width of the channel. Here with red and blue curves, we have actually measured the spectra at different positions and confirmed that it is in fact conforming to the Enstrophy cascade. And then we measure the friction on the rough wall. Now, to measure the friction on the rough wall, you not only need to measure the viscous stress, but also the Reynolds stress. Earlier, you could just get away with the viscous stress because at the smooth wall, Reynolds stress goes to 0. But at the interface of the rough wall, there's actually substantial contribution, in fact, dominant contribution from the Reynolds stress. So you have to use the technique of particle image velocimetry, which is what we used over here. And we measured for many, many, many different roughnesses. Smooth wall, there's just one kind of smooth wall. But rough wall, you have to change the roughnesses. So it involves a lot more of work. In any event, once you go through all of that work, the prediction from the spectral link is that if the spectral exponent is 3, then friction scales as roughness to the power 1. Not 1 over 3, but to the power 1. It's a linear scaling. And it's very, very different than the 3-dimensional things that we are used. So here is our data. Here you can see log of friction against log of Reynolds number. This is the smooth wall data for reference, where that follows the new Blasius scaling. And in different colors, we are showing you the data for different values of roughness. This is the roughest pipe, the second roughest pipe, the third one, so on and so forth. Sorry, I used the word pipe, it's this soap film channel. And you can see that we are confining attention, to the large Reynolds number, where we are looking into this regime where the friction is independent of Reynolds number, but clearly depends on the roughness. So if I now take this asymptotic value and plot it against roughness, which is what you're seeing here, log of this asymptotic value against log of roughness, here is the slope of 1. And you can see it's very different than the 1 over 3 scaling. And these results are in very good accord with the theoretical prediction that when the cascade is Enstrophy cascade, the rough scaling is in fact linear, not 1 over 3. Okay, so to summarize the different things that I said, the basic kind of an approach of the spectral link is that if you take a typical, I don't know, textbook of turbulent flows, Pope or whatever, you'll see that there's a separate chapter devoted to macroscopic properties, things that engineers are interested in, like friction. Also, this is the famous Nikuradise curve that we discussed. And then there are other chapters devoted to things that perhaps physicists and applied mathematicians are more interested in, which is the spectral structure. And what we have really done, so these are two kind of separate entities. And what we have really argued is that these two are but manifestations of the same thing, and in fact are inextricably connected with each other. And that's the very notion of spectral link. So because the spectral structure is theoretically much better understood than how friction behaves, we take this as our starting point and then predict or try to predict how the friction is going to behave. Of course, ultimately, all of these things are going to be tied to some behavior of the Navier-Stokes equation, which perhaps someday we'll understand, but for the time being, we are very far away from it. So that's the approach that we have taken in terms of trying to make some interesting new predictions and trying to understand problems using the perspective of spectral link. So in very brief summary, we took the Nikuradise diagram and we looked at the various salient features of the diagram, and we constructed a very simple model to try to understand these different features of the diagram. We were able to qualitatively understand things like hump and bellies and quantitatively predict the empirical scalings of the smooth and rough Blasius and Strickler. That led us to explore friction in 2-dimensional flows. For smooth walls, we were able to show that Enstrophy cascade gives a new Blasius scaling, and inverse energy cascade gives the same scaling as in a 3-dimensional flow. And for rough walls with Enstrophy cascade, we were able to verify a new scaling for the Strickler regime. If I summarize everything in just one line, I would simply say that macroscopic properties, today I talked about friction, but we have done other work also. Macroscopic properties of turbulent flows. If you want to predict that, a pretty decent starting point would be to just look at the spectrum. Macroscopic properties are tied to the spectrum. I have in the abstract of the talk a few references. Here are a few more over here. If any of this work is of interest, I would encourage you to take a look at any of these papers. You can go to my webpage and all of my PDFs are there. I publish very few papers, so it's very easy to find my papers if anybody's interested. And if you just indulge me for a few more seconds, I'll conclude on a philosophical point. So this is a quote from the great British statistician George Box. He was talking about statistical models, but I think it's valid for many other things we also do, said all models are wrong, some models are useful. So at the end of the day, I made some very, very simple assumptions, utterly simplifying assumptions to tackle a rather difficult problems. If we go into the nuts and bolts of it and we say, is this assumption exactly correct? Can you really justify it? I would say no. In that sense, that model is wrong. But I hope I've been able to make a reasonable case that it's a useful model to try to understand some aspects. With that, I thank you for your kind patience. And if you have any questions, I'll be happy to try to answer them.
Okay, thanks, Pinaki. I think you are modest. These results are very fascinating to me, and I guess to a lot of people. Okay, so thanks for a very nice talk. And I think very interesting results to me. I mean, these are all new to me.